Hello everyone. This paper is about application of a Gaussian filter to smooth optimization of freeform grid shells. The animation in this title page is showing two optimization of the grid shell to minimize the total strain energy. The left one is ordinary optimization process by using one of the Quasi-Newton methods. The result you get is rough and jagged. The right one is optimization process by the same Quasi-Newton method, but it is applied along with smoothing method proposed in this paper. Obviously, the result you can get is much smoother. How can you get it? This is what I'm going to talk from now. Let's think of typical 3 steps in the design of a freeform grid shell. First, an architect creates freeform surface by a modeling software such as Linus. Second, if you think a grid shell is good for structure, the grid must be defined over the freeform surface. Then finally, you will start optimization for the structure. If the freeform including grid framing is somehow parameterized utilizing mathematical model such as Bézier or NURBS, the structural optimization can also make use of control points. However, in practice, even today, the design steps between architects and engineers are not always so integrated. Of course, you can start structural optimization without parametric modeling. You just use all the coordinates of the grid as design variable, so no big deal. However, the problem is the solution geometry is often rough and jagged in such cases. We want an optimal solution that keeps the smooth surface like the original one. So let's see how we can control the smoothness of the geometry without parametric modeling. The proposed methods to get smooth optimization optimal geometry for grid shell is based on discrete convolution, which is used for signal low-pass filtering or image blurring. It is only an analogy. Let us suppose that the grid shell structure mainly consists of quadratic grid and almost uniform and almost regular, so that we can see the grid shell as a two-dimensional data that have value of z coordinate. It is like a discrete data of a surface wave. With this analogy, it is easy to understand how we can filter off high-frequency components of the geometry. The two-dimensional Gaussian function is given by this, and it is commonly used in image processing for smoothing, reducing noises, and blurring. Here the standard deviation of the probability distribution sigma is assumed to be 1 to get the discrete matrices in the next slide. These are the commonly used discrete kernels given in the matrices form for size of 3 by 3 and 5 by 5. The most straightforward way to apply smoothing technique to a grid shell's curved surface can be given by the convolution of the global z-coordinate of the grid shells and kernel function. Z on the right are the original z-coordinate and the updated z on the left are the smooth z-coordinate. However, in practice, the node in grid shell model is usually not stored in any useful order, but all you need to know is the indices of the neighboring nodes for each node, corresponding to the size of the kernel matrices, which is denoted by sigma Sij in these expressions. Now we recall that initial freeform should remain as the base outline of the desired shape. Therefore, it is more practical to use a relative z-coordinate from the original ones, rather than the absolute coordinates. Finally, applying the previous equations to the relative coordinates yields the convolution equation that smooths the modified portion of the geometry. This method can be applied in a very general framework of structure optimization because The proposed method can be implemented in the form of a preprocessor for the structural analysis, so that it is executed every time optimization program calls structural analysis program. Now we are going to see two test cases from the paper. All the test cases in the paper are selected from two aspects. One is that form find cannot be applied. All test cases have cantilever portion. The other thing is that statically indeterminate portion may not have a unique solution, and that tends to result in rough and jagged surface by the ordinary optimization. A portion supported by the branch column tends to have such issues. The setup for the structural localization are almost the same for all cases. Design variables are z coordinates of the grid shell node, except for all or part of perimeter nodes and supported boundaries. Objective function to minimize is total strain energy. Constraints are constant state quantity and upper and lower bounds for some of the z coordinates. The initial geometry in this test case has undulated surface repeated in circle. Figure A is initial geometry, B is an optimal solution without filter, C is an optimal solution with 5x5 Gaussian filter. The clear differences between the solution with and without filtering process shows the effects of keeping the basic smooth surface. However, in this case, the solution with 5x5 filter shown in C look way far different from the original intent. So in D, the D coordinates variables are constrained by adding the bounds for movement. This case successfully demonstrates that you can select a balanced solution between the improved structural performance and your preference to the initial idea. The last test case, the complexity is increased as shown in the initial geometry in A, by curving the ridge and valley lines as well as spanning more than half of approximately 40 meter overall length. A jagged geometry seen in the solution B would be hardly acceptable from the practical point of view. In contrast, smooth solution in C can be a good starting point for further design development. To summarize the work to conclude this presentation, I would say the proposed application of low-pass filtering can effectively work to find smooth optimal solution in line with original designer's intent. And some more points are noted here. Thanks for your attention.